Where's my mouse? Hello, chat. Yeah, hi guys. Hi guys. Whatever. Yeah, we're doing. I'm just gonna be going through like some of the lecture material in intelligence autonomous systems for the exam on first day, 2 days. Oops, that's not the button I wanted to press. So we'll do that, and yeah, I don't know. The morning was a bit cooked today. I got fucking nothing done. Well, I did do some dishes. Basically done most of all my dishes. I just had a huge fucking pile, which has been piling up for a very long time. So yeah. So there's 2 old exams somewhere here. I guess 3 actually. Exam and test exam. Yeah, Wednesday. Feel free to bring a calculator. I will. Knowledge questions about key terms, e.g. name components of behavior trees. Ability questions, e.g. design a simple PTFTCM with some specific functions. From us is intersections it will approach. Slides to understand questions to learn the course. To new scenario. Yeah, cool. So yeah, we're gonna be spam reading for them a bit. And there are these old exams here, so we're just gonna open them up. I don't think I've put them on my iPad yet. I should probably do that. I have most of my lectures. I've added most of the lectures to just because I went to them. There are a couple I missed. I think I missed like 2 lectures or something. One I know there was a scheduling conflict, and another one I just don't remember entirely why I missed one of them. I know one. I think I missed one just because I literally like looked at the wrong thing in the schedule. Let's see, modules. I'm just gonna put the exams on my iPad. Unos segundos chatarinos. Here. Let's put it in the right course. That one's 20, now 21 and 23. That's fun and interesting. They have very recently redone this course, or like for this year, they've basically redone this course. So some of these questions are not super relevant, which is fine. I need to go and grab my glass of water or my so give me 1 second, chat. Where's my calculator? My calculator's up here. Where is? Okie doke. I'm back. Wait, I need to clean my glasses. Give me 1 second, chat. I'm sorry. Okay, dokie. Perception, color space, So RGB and the fucking hue thing guy. Wait, what is it called? RGB hue. Color space, not RGB. Why? Well, yeah. CMYK. Yeah. Cyan, magenta, yellow, black. Why isn't it CMYB? What the fuck? Magenta, yellow, and black for printing. Specific hardware. Yeah. Cool. Yeah. Convolution. I mean, I know how to do this. I know how the convolution works. Sort. Yeah. It's supposed to be on this format. Yeah, I guess. Okay, I guess it makes sense. Because this isn't the. Because when you do convolutional neural networks, you apply filters to. So yeah, that one's doable. How do they represent color in red, green, and blue, and then in yellow, magenta, Y, CMYK, cyan, yellow, magenta, and black. Okay. Yeah, fuck it. Let me do some things here. Ransack stand for, what do we use ransack for? Random. Oh my fucking god! Wait, my brain. It's like for a tree thing, right? Ransack. I'll Google this at some point. Random sampling consensus. Yeah, algorithms with. Yeah. Get a. You see where a thing points to estimate parameters of a mathematical model from a set of observed. That all makes sense. Leave to affordance of the object cup. So I assume a cup does not have a little hoop. So I don't want to do this. I'm gonna write it on the thing, or GB and CMYK. Red, green, blue, cyan, magenta, yellow, black. I assume those are the answers that they're looking for. What do they represent color and are they related? So RGB is used on like computer screens because each like pixel has 3 small lights that, when combined or when the brightness is adjusted, my computer screen is extremely dirty. Okay, let me scroll a little bit down here. Yeah. How are they related? Well, yeah, you can't translate between them. CMYK is used in like printing. Which I know, Googled it. Yeah. I don't know what else about it. I know you use it in other applications, but I couldn't really tell you which ones. Wait, which exam is this? This is 22 one. Let me go back and open 21. List the 2 color spaces we have discussed. Yeah, RGB, EMYK. With red and blue, or with cyan, magenta, yellow. How would you find an object is green? I don't know what that means really. Wait, this is a different exam from the one I have here. Like, what the fuck? One here. Fuck, okay. I don't know, I don't know. We'll do a bit of convolution. Why not? That seems fun. Boom, 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 boom. Should we do padding? Let's do 0 padding. Well, on one of them it doesn't really fucking matter, but yeah. Here. I don't know what's considered like the standard thing to do. I'm just gonna add 0 padding on this side and on. It's more a formality on that side. And then what was our filter again? 1, 0, minus 1. Can do this justice, something like really annoying. Being so extra at the moment. Let me see here if we can. This works. And I can move it like this. So that mostly works. So yeah, I'm sorry you guys can't see this, but yeah, so 1. Oh no, don't do that. I guess we're gonna need to have to put it above then. Fine, let me do that. So this here is minus 1. I don't know if you should do double padding. The singular padding, I think it's fine. And we have here just. Can I get my fucking black pen? There we go. Oh no, I already like this one. So this one is then 0. This one is 0. Just sliding the window across. This one is 0. This one is 1. This one is also 1. And then the rest of them will just be 0. 0, 0, 0. So technically here we would need double padding out here. Over there, this one there will also be minus 1. And this one can't have any. Yeah, like this. So yeah, depending on how you. Yeah, that's the convolution. Move it down here and then this thing bigger. Sure. Convolution there. Finite state machines. Boom, 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 boom. I'm just trying to. What is the full formal definition of the finite state machine? Oh, I don't know. What like the full formal definition would be? Please write something down. Um, I'm super curious. Let me go see if we can find it in the lecture. Control F finite. Finite state machines. Let's see here. Where's the PDF then? Oh, it's down here. Cool. Here, def. I don't think we explicitly define as the formal. Yeah, no. It doesn't explicitly say or definition of finite state machine. My God, Giga Scorpion. Okay. That's what I'm done. Right. Okay, cool. Good. Just need some bullshit. Turnstile. None of this. Push is lock. Coin unlock. Push lock. And if you try to put a coin in, well, this is actually a very nice example. I like this. Tables to things. That's actually a really illustrative example to just show what it means. Times it. Yeah, okay. I'm gonna take a small break here. I just got here, but I just you know, feel. I just gonna go refill my water. As it is currently empty. This needs a just need a moment. So I'll see you guys in like 2 minutes or something. I'll bring up the BRB screen. Then we'll continue reading a bit about finite state machines together. Okie dokie. I feel a little better now. I just felt like I really wanted to brush my fucking teeth, you know? When your mouth just feels weird for whatever reason, right? Like it's just like, blah. So I feel a little more freshened up now, which is good. And then I have a electrolyte mix here. Tastes lemonade. I realized I haven't had one in a while. And my brain wanted like the fucking like, hey, fucking like I brought some fucking Pringles yesterday because they had the fun flavors, the hot flavors, which they usually don't have. So I got baited by that. Finite state machine is a mathematical model of computation. Can exactly to be in one state. The ability to be in exactly one state of a finite set of states can change states based on input on some input stimuli. I don't know if you could. I'm gonna call it a stimuli. I think that makes sense. To change. Let me actually put on a grid so I can write. I can like get some amount of fucking practice of just like writing straight. Much as like you'd think that I was able to do that at this point, having used this damn iPad for a few years, but apparently not. Apparently that's the thing I struggle with. Oops. Defined. So let me see here. Oh, the other part of the F is just gonna. I'm being very pedantic here, but that's super annoying. Finite state. Coming along. Machine. FM. FM is just a dot there, the middle of this, and then move it all. So what I'm doing right now is not really helping study better, but it's one of those things which annoys me. So just want to spend some time. I think this might be one of the reasons why I tend to not like to go back and read my shit. Just because slightly annoying to just read through my notes. It can be quite as pedantic. I say and then become incredibly pedantic again. That's such a bad Yule. Input. Stimuli. Transition. Like highlight the word transition. Does that matter? Doesn't really. I don't need to highlight that. It's fine. Decision. There we go. Sort of. Transition. List of by a list of its state, its initial state, and the inputs that trigger each transition. So a list of states. Its initial state and the transitions between the states. So that's like what defines it. Oh Lord. We had the state-centric view, we had the action-centric view. I don't think those words are specifically used. Yeah, we never used the word centric at any point in here. You know, my brain can use things to think of things. State-centric view and action-centric view. On the line, you fucking asshole. State-centric view. Looking at a to which, Elizabeth, to which state what actions can I take? That's my best answer. Explain the working principle of probabilistic data filter for localization. Use a diagram to support your explanation. Give one example of filtering approach, including coarse explanation of this particular approach. So, Kalman filtering is the first thing that obviously pops into my mind. So let me see here. Super annoyed at the fucking crackling noise this thing is making. Okay, it stopped. Hopefully for good. I don't think it's for good. Wikipedia. No. Holy shit, it's so annoying. It's actually so tilting. I can't do this. I can't do this shit. Holy shit, it is so fucking tilting. Having this thing just crackle in my fucking ear. Okay, so I turned it off. Let's see. Yeah. Let me continue. God, they wanted to get 90% of the points to get a 5. That's, I mean, because the fucking questions here aren't super difficult. So I guess it makes some sense. So when are sensors collect data when navigating this data will contain some amount of noise that disturbs there we go, that disturbs the signal. Thusly, I like the word thusly, some amount of filtering slash cleaning. Again, keep the things on the floor. Cleaning has to be made, has to be executed. Sure, has to be made. Kalman filter. Does this how do, because I know that what it doesn't, Kalman filter. Bring up like a little small YouTube video. Pokemon has an AI problem. Stop being distracted. I'm sorry, chat. Kalman filter. Should explain the Kalman filter. Fuck is that thing? That thing looks awesome. Okay. Okay. Cool, bro. Yeah, it's fun. Where the fuck did I click on that? I guess let's see. Let's give this guy like. Right, and then we'll make predictions of it. This makes sense. This is a good example. Mm-hmm. Hmm. I'm sorry, guys. I know you guys can't hear what the fuck's going on. Mm-hmm. Fuck it. Let me turn the audio on.
All
There we go.
right, now an hour has passed. What would be your best guess for where the car position is right now? And what is your guess for the car's speed? You could say, let me ignore all the imperfections of the word and follow this idealized dynamical system and see where it leads me. The math in this case is pretty simple. The car would remain at the constant speed of 60 km per hour, and after 1 hour, it would be 1 kilometer away from the starting position. Now, all of a sudden, you remember something. You actually have a GPS installed in the car, and that GPS can give you measurements of the position of the car every hour. Perfect! You check the GPS data, and it's telling you that the car is 0.8 kilometer away from the starting position. This GPS, however, does not measure the speed of the car. So now, here is a question. Which one of these two measurements would you trust more? The one you have predicted by ignoring all the imperfections of the word, or the estimate that you obtained from your measuring instruments? More interestingly though, can you combine both of these estimates to get a new estimate that is more accurate than both estimates individually? For instance, if you had to guess, you would say that the true position of the car is probably between the 0.8 and 1 kilometer mark, and as a consequence, the speed of the car should probably be lower than 60 kilometers per hour. But how much less than 60 kilometers per hour exactly? And where exactly in the interval 0.8, 1 would you say the car's position is right now? As you might have guessed, the answer probably depends on what we know about the size of the noise in our initial estimates, in our measuring instruments, in our model of the dynamical system of the car. The answer to this question is what Kalman filters are all about. As we will see, a Kalman filter is an algorithm for estimating the state of the system, for example, the speed and position of the car, using past and possibly noisy observations, and current and possibly noisy measurements of that system. More specifically, let's say that this is the underlying dynamical system. And let's say that this is the measurement that we get. So at every time t, we get a measurement that is a random variable yt. So you can see that yt is a linear function of the state xt plus some noise v that we model as a random Gaussian variable with a known covariance matrix q. In the toy example we just saw, h was the row vector 1, 0, because the only thing we measured through the GPS is the position. And that was the first component of our state vector xt. Kalman filtering is a two-step process. Here is how it works.
Should write something.
The first step is called the prediction step.
God, I'm cold.
In
I
this
need to
step,
get
you take
I need to grab a shirt or something. I'm trying to see if I have one down here somewhere. It doesn't look like I do, so I need to go upstairs and grab one. I am cold and a little bit tired. Yeah. Give me unos momentos, chaterinos. All right, chatty. Chat, I'm back. Wait. Yeah. Does it work?
Take whatever prior.
Yeah, but. Oh. I think I'll. This. Sure. They do look a little bit silly, but that's fine. I am used to looking a little bit silly. I have a cow with me. His Otis. He is my son. I felt like I needed something soft to to chill with. All right, let's continue here. Yeah.
Estimates you had about the state of the system, you run these estimates through the idealized version of the dynamical system,
Yes.
and that would be your prediction for the state of the system at the next time step.
Yes.
I'm going to mark these estimates with a minus sign upper script. The reason I do that is because this will not be our final estimate, since we have not yet incorporated the information that we get from our measuring instruments. Another important thing we have to do in this prediction step is to think about how our noise covariance matrix propagates through the system. In the case where we have perfect estimates of our state variables, i.e. when sigma t is 0, the only uncertainty is going to come from the perturbation to our dynamical system, i.e. from the matrix P. In general, though, sigma t would not be 0. So when you run this sigma t through the idealized system and you work out the math, you realize that we need to add an additional term, a sigma A transpose. So what does this mean for our toy example? Well, in the prediction step, we simply predict that the car would be in this yellow spot. So now the question is,
yes,
how can I incorporate the additional information I get from my measuring instruments to update and improve this prediction? That is done in the second step of Kalman filtering, which is appropriately called the update step.
I wasn't going to take an entire fucking course on Kalman filtering here today, but.
So we're talking about Kalman filters, but we're going to start with something called recursive filters.
Mm-hmm.
And the first one isn't going to seem much like a filter. It's a recursive expression for the average. So just taking an average of some data points. So a recursive expression or the average. Recursive just means it's changing in time. It's changing as you march forward along a data set. So first, let's just assume that we've got K data points. And these could be, we'll think of these as scalars for now, but later they could be vectors. So we've got x1 is the first measurement, x2 the second, so on, all the way to xk. We've got k data points. So then x bar k is going to be the average over these k data points.
Okay.
So what is it? It's the sum.
Yeah, you sum
x1
up
plus
and
x2 all the
divide
way
them
to
by the amount you
xk,
have. Yeah.
divided by the number of points. This isn't anything you don't know. This is just an expression for the average, but it does take in all k points. So we'll call this a batch expression, which is different from a recursion expression, meaning it takes the whole batch of points. So if k is large, let's say greater than 1,000,000 or something, then this could be computationally expensive.
Yes.
Because let's say now we get 1,000,000 plus 1. Now you got to add all 1,000,000 plus 1. And we don't want to do that. We want to do something that could be quick on the fly, something that's especially very quick to compute for something on board a vehicle or any kind of craft or some kind of small CubeSat. These things don't have the computational power of the cloud or the ARC supercomputer, or even sometimes.
I'm sorry, I'm being distracted here.
This is one thing I say to all students, that to be a really good mathematician, you have to be lazy. Okay, so you look at that and you sort of say, right, you could go straight in, integrate it, put the values in, get 0, or you could step back for a minute and say, is there a trick I could use that gets the answer without having to do a lot of work? And the answer is yes, there is. So before you dive into something, sit back, look at the problem and see, is there a clever way I can do this that'll save me time? This is one thing I say to all students, that to be a
Yeah. Tiny piece of the cover. This thing is slowly disintegrating. It's held up fairly well, right? This iPad is like 6 years old, I think. It's been abused for like almost every single day for like many hours a day. Yeah, it was totally worth. Sure, bro.
Our iPhone. If you've used Arduinos and things, they've got little microprocessors, and you want to try to make the algorithm as simple as possible so that things can work in real time. So we are going to be concerned about how computationally expensive is this. Adding up 1,000,000 things and then adding up 1,000,001 just doesn't really cut it for us. So we want to write a recursive expression, meaning we want to write x bar k, the average over k, in terms of the average, the previous average, x bar k minus 1 plus something new. What is x bar k minus 1? This is just the sum over all of these up to.
I'm feeling conflicted, chat, because I want to keep watching this. Right? Comma filtering is important, right? There is, I mean, you can take a fucking course on it in some sense. But yeah, you use your data to make predictions about what you know about the world. So you keep in mind what you think was likely to happen, and then you take in the data which you accumulate, and then you update based on the data that you receive, and that will have some amount of a normal distribution to your noise, likely, unless you know something else about it. But if you knew something else about the noise, you were pretty likely to be able to just remove it. Yeah. Does this by updating or predicted position based on the the new sensor data coming in. Sensor data coming in. Sure. We can talk about the Voronoi graphs. That part's likely to show up again. Voronoi. A Voronoi graph. What's the difference between a graph and a diagram? Diagram versus graph. Okay. So graphs are two-dimensional. Is that what we're saying? Seems to me to be what we're saying. I'm sure though. God, I look like shit, don't I? Yeah, that's kind of fucked. Alrighty. Alrighty. Well, fuck. This is the one. Alright, cool. Let me continue. What is the graph? I don't care. Go away. Vornographs. A Vornograph. It's a graph. It's a method. It's a or graph. That keeps tat the H in there. That keeps keeps equidistant that keeps equal distance. Let's just write it that way. Keeps equal distance to all obstacles, obstacles. Making sure that all that a robot keeps as safe of a margin possible, reducing the risk of a collision. It has some potential downside, as it can be seen as a very conservative navigation strategy. As it could forego speed slash optimality. Put that in air quotes. Since it refuses to cut a corner, so to speak, and then literally. Boom, boom. And then I could draw one. Or they constructed offline. They can be constructed offline if you just have a map. Environment online. So if you have the ability to measure distances, you can then make sure that you keep equidistance to your measurements. And moving then away from moving towards open space, or moving away from your or wherever you need to go. Three types of autonomous systems. Oh, we mentioned that. For each of the three types of autonomous systems, please describe three feature assumptions that are unique and distinct to each of them. Each of the three types of autonomous systems. Types of autonomous systems. What do they mean by that? Transit, stub, or multi-head? Multi-homed. Well, this isn't exactly what we want. I don't know what they mean by that. Yeah, I don't know the answer to that really. The automatic planning related to robot skills. So automatic planning automatic planning bases its plan on its available robot skills that require preconditions preconditions and sets the world's postconditions. The effect the skill has on the world. Skill execution has on the world. Skill, come on, skill execution has on the world. For the second type of autonomous systems, we have described picking as a 6-step process. Second type of autonomous system. What do you mean? What the fuck are you? Are we talking like, you know, on a conceptual level, like levels of autonomous systems, or are we talking like, you know, you have like arms, or you have like a mobile platform, or something like that? Because I have no fucking clue what they mean. Describe each key step in detail, possibly providing a simple example. Oh, that's on our slide. Reach, grab, move, place, grasp would be a better word. Application questions. Consider yourself the CTO of some robotics, Chief Technical Officer, I assume. Your startup is asked by the supermarket chain ICA to design a robot that would help elderly in an ICA store to do shopping. Assume the following constraints. The robot is expected to serve as an autonomous shopping trolley. Oh, that's fucking awesome, actually. Collect. Wait, that's actually so fucking. It's put a gripper on. What the fuck? Wait, why isn't this a thing? There's plenty of reasons why it's not a thing, but still, collecting purchases without the need for physical assistance by the human, i.e., somehow getting the items from the shelf into the basket. So grippa. Grippa. That's write that better. Gripper. Grip. What the fuck? Can my fucking pen like not fuck me in the ass? Gripper. Mobile platform. Bro is just here on with a basket. Wants to point to shopping items and just stroll around to look for interesting things. To look for interesting things. So camera plus perception. Perception would probably do the trick. To guide the human to a specific location of interest. The map. To do the item collecting fully autonomously. Yes. World representation of world model. specify necessary hardware, specify the robot skills necessary for this task, specify the reasoning necessary for implementing the skills, specify robot interaction relevant for the task, specify how the perception should be implemented. You should be precise enough so that the programmers can start to implement your specs using ROS. You can assume that your programmers know ROS and the ROS libraries. Basic functions such as object detection and find object 6D location, grasp object at 6D coordinate, place object at 6D coordinate, navigate to 3D coordinate and are readily available. Let's stick to the order above for the task. Start simply expand your robot specs incrementally by doing through this list several times. They put a gripper on a fig and they, oh my god, that's awesome. Ser det Ika? Don't think that there might be an Ika, I don't know. Autonomous shopping cart. There are people working on this, which is cool. Typing out the edge. Stroller hack.
Imagine walking into a store and having a shopping cart that follows you like a loyal pet. Autonomous shopping carts equipped with AI technology are set to change the way we shop. These innovative carts navigate through aisles, intelligently avoid obstacles, and even help you find items on your shopping list. They communicate with your smartphone, offering personalized deals and recommendations as you shop, making the experience seamless and efficient. As retailers adopt this technology, it's just one step towards a fully automated shopping environment.
What is happening here?
Where convenience reigns supreme. Imagine walking into a store.
So this lady might have just shown us the future of grocery shopping, and I honestly think a lot of people might be out of a job after this.
Can we take in how crazy this is? The scanner and everything. Just grab something, scan it, and place in cart. Crazy.
And after showing how you can buy items on your own, you can even remove things from your cart by yourself, leaving everything automated by you in the grocery store. How much would you tip this cart? So this lady
Going to be a maintenance nightmare. This person yelling. Playlist to romanticize studying physics. Yeah, that's what I fucking need. There. Fuck it. Let's listen to this chat. Actually, you guys are not allowed to listen. Let me see here. Where were we? Do. Yeah, this is fun. I don't know the whole thing though. The more human something is, we like it until we don't, and then I guess that it is just human at some point. Conversation. Human see human trait in Robert. Okay, and then you do this last guy here. I should sit down and do. I don't want to do it right now. I'm just thinking I should eat food today. I don't really know what I want to eat yet. So that's the 21, which 20, yeah, no, 21 here. What is a feature detector and a feature descriptor? Name the feature descriptor, introduce and explain. We didn't. Random sampling consensus. Didactic gesture. 2 possible preconditions for a pick skill. The group is empty. Post conditions, group are empty. Object at location. List 2 relevant parameters of the state space that are changed by pick skill. I mean, just fun. What the fuck is this song? I can't recognize it. It is Hans Zimmer. Jacob's piano. Cool. Study in a human way. Let's go, bro. So I can go. I don't have much to eat today, so one of the things my brain is thinking about a little bit. So let's see, it's what's 21. I just very quickly scrolled through it. It's very much the same things. I wouldn't want to just like spam some. And the last guy here, perception. Yeah, the fucking color spaces just aren't mentioned. Scripture, was this the one? Did they use the same fucking question 2 times in a row? Yes. Looks like they did. It's the exact same question. Basically, yeah. Yeah, same thing there, so I'll just do that twice. Maybe I'll tomorrow, remember once. Define for 5. The long answer should be, yeah, that makes sense. How many 100 points? Okay. At least 75 points, which should be attainable. Yeah. I'm getting a little bit hungry. How many points for 60 points here? Yeah. So make a good thing here. It's fun. I mean, yeah. I mean, you're never gonna get the whole 60 points from here. Ridiculous, but yeah. I don't know. I'm excited for this exam. I think it's gonna be fun. Feeling a little sick, but just a tiny amount. Otherwise, I don't know. I don't know. Been streaming for soon to be 2 hours. Yeah, we're gonna do those. I'm just gonna scroll through some old Dr. Docker shell. Yeah. I mean, I should genuinely start up these things again. I don't know if I can. I want to buy the computer, man. I want to buy the computer. Should I buy the computer? I probably should buy the computer. Right. I mean, because if I buy the computer, I want it to get it before, like, things start out. Right. I want to get it soon enough, So I'm gonna fucking do it. I'm gonna do it. Yeah. Otherwise, I don't know, chat. I feel like I should probably eat dinner like a little sooner today. I think that makes sense. I'm not sure what I'll make. No more. There. I mean, I'll bring it up on my iPad and I'll scroll through there probably. But yeah, I am thinking in terms of food at the moment. I didn't really have a proper lunch. That's where my brain is at. Yeah. So I don't know. It's been fun 2 hours. I might be back after I've eaten and stuff. Actually, this is sort of fun. I want to spend more time on it. I just want to hit the gym at some point because I haven't been to the gym in like a week. Life happened mostly. You're going to die. Try to like things more. Yeah. I think that's it for now. This has been great fun. I know maybe it wasn't the most engaging stream in terms of the things you guys could look at. Because I didn't share my iPad screen. But yeah. Taking a break here, I think. Yeah, because I need to make food. Make proper food for like days. A bit of a project, and then a gym, and then I don't know. We'll see. So that's where my brain is at. Because I'm sort of hungry. So you should make food. Probably just so I can. I need to spend some amount of time to figure out what I actually want to eat and plan some stuff. And they usually take a while for me to make food because I'm bad at making food. And then we'll see from there what I'll end up making. So I will. I'll see you guys around. Thank you guys very much for watching, and I will talk to you in a bit.